Okay, so chapter 16 is about going in circles again, but now we're going to worry about how fast you go in circles. And there's two ways to measure speed. You can measure in how fast you're actually moving, like in problem number 1, you're in the Space Needle, which turns 1 revolution per hour, 1 circle per hour. So how fast are you actually moving through the air, like if the air is in your face, how fast would the wind be hitting you? Or we could also measure how fast your angle is changing. If you're going 1 revolution per hour, that's clearly 360 degrees per hour, right? Because 1 circle is 360 degrees. So that's 360 degrees per hour. Of course, you got to be really careful with minutes. They immediately change things to minutes, so you got to worry about units and everything. But it's the same idea. Degrees per hour, revolutions per hour. A revolution is a circle per hour. We could also say if it's 360 degrees per hour, 360 degrees is 2 pi radians. So we could also say let's see, 1 circle per hour, or we could say it's 2 pi radians per hour. And normally you don't have to write radians, because if you use radians, the units just work out nice, but it's nice to know what we're talking about. So, and you can abbreviate it by rads or something, so it's 2 pi radians per hour. All of those things are angular speeds. How fast are you going in a circle? We have no idea how fast you're going. That depends on the radius, which they say is 21 meters in the Space Needle, which probably is. But how fast degrees per hour is just how fast you're turning in a circle, right? How fast you're going depends on how far away. The bigger the circle, the faster you're going. Okay, so this has a word. This speed, this angular speed, is given the Greek letter omega. It looks like a W, but it's like got curvy in the bottom. It's not sharp in the bottom. And that's the Greek letter omega. It's the small omega, the non-capital omega. And that's the angular speed. Okay, so this is called how fast you're going, how fast your angle is changing. And again, there's different ways to measure it. They also, I think, call it your, angular speed. It could be in radians per second, radians per hour, degrees, circles per hour. RPMs are really common, rotations per minute. You've probably heard of RPMs. That's how they measure, like in a car, how many complete cycles it goes through, rotations per minute. So RPMs, those are all angular speeds. If you want to know how fast you're actually going, then you need to know your velocity, which depends on your radius. And to work that out, we can also say, so I'm just going to go through the general formulas here, that the angle you turn, which of course angles are measured by, they use theta, the angle you turn is your angular speed times time. So it's just like the distance you go is your velocity times time. The angle you go is your angular speed times time. And this works for any units. If you want circles per hour times hours, it tells you how many circles. If you have degrees per second times seconds, it tells you how many degrees you went. Of course, radians are a natural unit to use, but you don't have to. But as soon as you have a radius in the formula, you have to use radians. Now, from the last chapter, okay, this is one formula we're going to use a lot. From the last chapter, we know that the arc length you go is the radius times theta. S equals r theta. We figured that out. It's another formula we're going to be using a whole lot. The arc length is the radius times theta. This only works in radians. As soon as you have an r in the formula, the radius, you have to use radians. Theta has to be in radians for this to work out. Otherwise, you have to deal with units. And let's combine those two then. Theta is omega 2. Is omega t. So S is equal to r theta, which is r omega t. If we divide both sides by t, divide by t, divide by t, S over t, that's like distance divided by time, which is like velocity. So S over t is equal to r omega, and distance divided by time is like velocity. So the other formula we're going to use a whole lot is that the velocity is r omega. So those three formulas are going to be used a whole lot. How fast you're actually going as you go in the circle, it depends on the radius, and how fast you're going, how fast your angle's changing. And again, this works out perfectly if omega is in radians. If omega is not in radians, then we got to worry about units, because here if r is in meters and omega is in like radians per second, we get an answer in meters per second. So radians is a natural way to use, natural unit to use for all these, so we got to worry about that. And of course we know you got to always remember that 2 pi radians is the same as 360 degrees. So 2 pi is the same as 360, and you just divide by 2, so pi is 180. So if you want to convert, you just either multiply by 180 over pi if you want degrees. So if you want degrees, you multiply by 180 degrees over pi. What you want is always in the top. You want degrees, you put the degrees in the top. If you want radians, you multiply by pi over 180. And again, you want radians, put the radians on top. So this is all stuff we're going to be using this whole chapter. Okay, let's actually do the problem. So 16.1, part A says, through how many radians does it turn in 100 minutes? Okay, it goes 1 revolution per hour. So like we said before, 1 revolution per hour. Let's change it to radians. A revolution is 2 pi radians. So that's times 2 pi radians per revolution. Just using our old unit conversion skills, so we know revolutions cancel. Now we want minutes. So in 1 hour, put the hour in the top to cancel out this hour in the bottom is the same as 60 minutes. So this equals then 2 pi, let's see, 2 pi divided by 60. And now will tell us how many radians. See, the hours cancel, tells us how many radians per minute. So 2 times pi divided by 60 equals, and I'm going to keep lots of decimal places, 0.1047, 0.1047 radians per minute. Now they ask us how far it goes, through how many radians does it turn in 100 minutes. So we want radians, which is an angle, so we use this formula. So, oh, and this is omega. This is how many radians per minute, which is how fast the angle is changing. That's our omega. So theta then is omega t, which is 0.1047 radians per minute times minutes. We want 100 minutes. And that's easy math. Now again, minutes cancel. We're left with radians. 100, just move the decimal place over. So 10.47 minutes. We can convert that to minutes and seconds if we want, but yeah, just leave it as 10.47 minutes. Sorry, 10.47 minutes. 10.47 radians. We want to know what the angle we turned in. We returned 10.47 radians. Okay, that's part A. Now part B. How long does it take the restaurant to rotate through 4 radians? Okay, so let's think about it. It goes 2 pi radians in an hour, 1 circle per hour, which is 2 pi radians. Pi is 3.14 about, so 6.28 radians per hour. So we want to know how far it goes in 4 radians. So a little less than an hour, right? It takes an hour to go 6.28. We want to know how long it takes to go 4. Okay. So we want time. So let's see. We know that the time, well, let's use our old formula here. Let me just start from scratch. So we know that theta is equal to omega t. We want t, so divide both sides by omega. So the time it takes is the angle we go divided by our angular speed. Just like time it takes is distance divided by velocity. It's the same thing, right? So we want to go 4 radians. So 4 radians. We worked out from above that the angular speed omega is 0.1047 radians. I don't need to write out radians the whole time, but I did on top, so I might as well do it now. Radians per minute. Radians cancel. Minutes on the bottom is like minutes on the top. So we just divide 4 by that. 4 divided by 0.1047 is 38.2. So about 38.2 minutes, which is about right. Right? Takes an hour to go 6.28. How long does it go to go 4? About 2/3 of an hour or something. So answer looks about right. Okay, so again, using these formulas, these 3 formulas, the angle you go is omega t, s equals r theta. We haven't used this one yet, but we're going to. And then just being really careful with units. All right, C. Now they say, how far does a person sitting by the window move in 100 minutes if the radius of the restaurant is 21 meters? I guess we don't use that formula. We want how far you go. Okay, well, the distance you go in a circle, the arc length you go in a circle, is r theta. The radius times the angle you turn. And again, this works perfectly if we use radians. So, how far does a person sitting by the window move in 100 minutes if the radius, okay, so in 100 minutes, how far do they go? Well, they asked that in part A, how many radians does it turn in 100 minutes? So, in 100 minutes, from part A, we know that the theta, the number of radians, was 10.47. Because it's nice that they didn't give us different numbers, we can use our part A. So 10.47 radians. So the distance we actually go is the radius, which is 21 meters, times radians times 10.47 radians, which is 21 meters, 21 times 10.47, which is 219.87, and its distance, we have meters, and again if we have radians, we just get the natural unit, so it's in meters. So 219.87 meters is about the distance you go. So, now they could have said, how fast are you moving? They should have. I don't know why they didn't. So let's pretend they did. How fast are you actually moving in a circle? Well then, we just say V is equal to R omega, which is 21 meters, and we already figured out that omega was 0.1047 radians per minute times 0.1047 radians per minute. So our units will be meters per minute, which, you know, whatever, we can use that. So 21 times 0.1047. I get 2.198, about 2.2. About 2.2 meters per minute. Again, that's a weird unit. Let's change that to meters per second. So we multiply by 1 minute is the same as 60 seconds. And it's going to be a really tiny number. So 2.2 divided by 60, okay, really small, 0.0366, let's say 0.037. So about 0.037 meters per second. So not very fast, which you wouldn't think. You watch a space needle moving, and it doesn't move very fast. Only about 0.037, what's that? 3.7 centimeters a second. Ends up being 2.2 meters per minute. So yeah. Okay, so that's how you do these. These three formulas you can use a lot, and converting back and forth between radians, and worried about inches, and just really be careful with units. A lot of these problems are just unit problems. So hope that helps, and as always, let me know if you want to work out any more problems. So thanks for listening.